Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on double and half angle formulas. This is the last lesson in my chapter for analytic trigonometry. And what we're going to focus on in this lesson is learning to evaluate using the double and half angle formulas. We're going to evaluate given angles as well as given a right triangle. And then we're going to focus on being able to verify and solve equations using the double angle formulas. So the way I started off this lesson with my students is I said, well, last lesson we talked about the sum and difference of two angles. So I said, why don't we just go ahead and simplify these using the sum and difference formulas that we remember. So I gave my students some time and, just to kind of work through this. So we had sine of theta, cosine of theta, if you remember, plus cosine of theta, sine of theta, and then ask them to simplify. Some groups were able to do it, where this can be simplified to 2 sine of theta, cosine of theta. And then this one, using the cosine formula, would be cosine of theta minus, remember that, sine of theta, sine of theta. And we multiply a cosine times a cosine or a sine times a sine, we get a cosine squared of theta minus a sine squared of theta. And then if we did the tangent, that would be, let's see, tangent of theta plus tangent of theta all over 1 minus tangent of theta over tangent of theta. And we can simplify that one more time into 2 tangent of theta all over 1 minus tangent squared of theta. So the interesting point is I asked the students, all right, so we went ahead and applied the formula and then we went ahead and simplified. So what exactly was the point of this? Like, why did we do all this? Well, another way we can write theta plus theta, it would be the sine of 2 theta. So what I just showed my students is you guys just created your new formula, right? You can see where the sine of 2 theta came from. And that's the same thing for the cosine of 2 theta over here. Here is one of those formulas, cosine of 2 theta. And then here is the tangent of 2 theta. Oops, forgot the 2 there. So what we did is, and we can do this for all the sum and difference. You could do this for the half angle formulas. But obviously for the sake of time and as well as for the complexity of the class, I wanted to kind of keep things simple. And so that's why we just kind of focused on, proving or at least showing the students where these double angle formulas come from. Because really, there's really not much else to teach here. As far as new stuff, we can see here are the formulas, right? And these are the formulas that you would find right in your textbook. Now, the only thing that sometimes confuses students is the cosine. There's multiple variations, but this is actually really important because when we're going to be doing problems, we're going to be using, or we could use all 3 of these variations. So first of all, here's what we got. How do you get these two? And then also, we'll talk about when we want to use one form over another form, but we'll talk about that later in the lesson. So to understand why those other forms come from is to really can think about why would we want those forms. So in this case, we have a cosine squared and a sine squared. Well, what if we only want our expression to be in terms of sines? So therefore, what I could do, and actually let me rewrite that. If I only want my expression to be in terms of sines, I can rewrite. You see, this is the only one that has a cosine and a sine squared. So therefore, I can apply my Pythagorean identities. So I can rewrite this as 1 minus sine squared of theta minus sine squared of theta. So now what you see is you have like a negative sine squared minus another negative sine squared, which is a negative 2 sine squared of theta. All right, and we could do the same thing if we wanted to write these in terms of cosines. So if I did cosine squared of theta, let's see, minus a 1 minus cosine squared. Again, that's the Pythagorean identity I'm using. Okay, and therefore you can see you distributed properties, that's a negative 1 and that's a positive cosine. So therefore that becomes a 2 cosine squared of theta minus 1. And you can see that both of those are still going to equal a cosine of 2 theta, and you can see them written out here just like that in that format. So we'll talk about later as we get through some problems, how that comes in handy and what that how that can be helpful. But first of all, I wanted students to kind of get a little bit familiar with these identities. And so what we started with is I gave them an expression. So I gave them one of the formulas and I asked them to basically figure out, is it the sine of 2 theta, cosine of 2 theta, or tangent of 2 theta? And then to go ahead and evaluate. So you can see here, I have 3 equations, or 3 expressions, I'm sorry. And basically what we want to do is write it as a single trig function, right? So we're going to write it as the trig function of a double angle. And then we want to be able to evaluate, because obviously we cannot evaluate pi over 12, 15 degrees, or negative pi over 8, at least based on what we are aware of at this time. So what we're going to need to do here is go ahead and use this double angle formula. So we recognize this and we say, all right, which one of these does it look like? So here we have 2 sine of an angle times cosine of the angle. Well, hopefully you can recognize that the only one it looks like is sine, right? The sine of 2 theta. So now what we got to do is kind of figure out, and this is where it kind of got a little tricky with students. We can recognize here that theta is pi over 12. So what we're really asking, what we're really trying to do to identify is we know that this is the sine, right, of 2 theta. So now all we're going to do is really plug this in. So this is the sine of 2 times pi over 12. Well, 2 times pi over 12 is going to be the sine of pi over 6. And then now, just using the unit circle, we can say pi over 6. That's going to be equal to 1/2. So you can see how that basically is. So really what we're doing is we're taking these angles and we're really just multiplying them by 2. So now in the next formula, we recognize this to be cosine squared minus sine squared. And hopefully just a little bit look up top to your answer. You say, oh, that's that right there. That's the cosine. So if that's theta, right, we want to multiply by 2 to get the formula. So if we have 15 degrees, I can just write this now as cosine of 30 degrees, right? You're basically just going to take this angle and multiply by 2. Well, cosine of 30 degrees, I know that. That's going to be the square root of 3 over 2. And then obviously you can see that tangent looks nothing like cosine or sine. And obviously it's in the terms of tangent, right? So you can see that, okay, that one's kind of obvious, right? That's the tangent of the double angle. So now I just need to figure out what my theta is. So again, let's do this one. So theta equals negative pi over 8. So then 2 theta would be 2 times negative pi over 8. Right, so therefore that's going to be a negative pi over 4. So really what I'm trying to figure out is the tangent of negative pi over 4. Right, so that'd be the double angle, right? That's exactly what you're evaluating for. And then knowing the unit circle, negative pi over 4 is in the 4th quadrant. It's going to equal 1, but since it's in the 4th quadrant, it's going to be a negative 1. All right, so that was to kind of get students a little bit more familiar with these expressions and how they work. And now the next one is to kind of go through a triangle, just kind of like what we did with the sum and difference formulas. However, in this case, we only really need to have one angle. So, you know, obviously sometimes we're going to have angles and we can just apply the sum and difference formulas for them. Or sorry, the double angle formula. But typically for a double angle formula, it's going to be most useful to either evaluate using this way or when given a triangle. And so let me kind of think, trying to think what I have here. All right, so when we have a triangle, the first thing we got to do is create the triangle. So we have tangent of theta equals 4/3, right? If we look at the sine formula, we have 2 sine of theta, cosine of theta, right? So I need to figure out, right, this is equal to 2 sine of theta, cosine of theta. Well, the only thing I'm aware of is tangent. So I need to figure out what sine and cosine is of theta. That means I need to draw the triangle. So I'm going to create an xy axis. I see 4/3 tangent, right? That's opposite over adjacent. And that immediately makes me think, oh, it has to be in the first quadrant, right? But the problem is sine is less than 0. Like we want to put it up here, but sine of theta is less than 0. So therefore, it has to be in the in the third and the fourth quadrant. So now I got to think, well, which one is it going to be in, right? Is it in the second or is it in the third quadrant? Well, obviously, if sine is negative and then this is positive, like tangent is only, you can see that tangent's positive, right? So tangent is only positive in the first and the third quadrant. So therefore, we can see that our triangle here is right there. So we can put our theta right there, and then we can put this as actually a negative 4 over negative 3. And you can see how that actually still produces a tangent of 4/3, right? A negative 4 over negative 3 is still a positive 4/3. The difference here is sine of theta is less than 0. It's a negative 4, because if you did it over here, yeah, that satisfies tangent, but it doesn't satisfy that. So that's why that one doesn't work. All right, but now we have our triangle, and hopefully we can use our Pythagorean theorem, or you can recognize this to be a Pythagorean triple. So therefore, that is going to, our hypotenuse will be a length of 5. And again, remember, hypotenuse is always positive. So now that we have the triangle, it's basically just, you know, good old plug and chug. Like You find it in, you plug it in, and then you chug away. But the chugging is not always as simple as we want it to be. So that we'll get onto some of those problems later. So let's just go, this one is rather nice, or at least not too bad. So I have sine of theta, which is going to be -4 over 5. And then cosine of theta, which is a -3 over 5. Okay, so now I remember that's really a 2 over 1. So you're just going to multiply straight across. So that's going to be a positive 24 over 25, as a -4 times -3 is a positive 12. Now for the cosine, you can pick really any formula that you want to. I prefer for evaluating to do cosine squared minus sine squared, unless there's something that I realize is not going to be difficult. The reason why I like cosine squared minus sine squared is just because it's easier to, typically it's going to be easier to combine your terms because you'll always have a common denominator because the common denominator will be the hypotenuse. So it's a little bit easier just to do the work. So I'll do cosine squared minus sine squared of theta. Don't forget the thetas. All right, so cosine is -3 over 5. Quantity squared minus sine is -4 over 5, quantity squared. Okay, so -3 over 5 is going to be 9/25, and therefore minus a 16/25. Okay, so that's going to be a -7/25. All right, then we get down to the tangent. So again, just applying the tangent formula. Let's see, that's going to be 2 tangent of theta all over 1 minus tangent squared of theta, right? So that was that formula that we figured out. And now again, we'll just plug it in. So tangent, as we already know, actually tangent's 4/3, right? So we just say 2 times 4/3 all over 1 minus 4/3 squared. Now here's where the fun starts to become. So a lot of times we worked on these, we can multiply by the conjugate. Sometimes we'll do fraction operations. So I'm just going to do fraction operations here, just to try to simplify everything. So I can do 2 times 4/3, which is going to give me an 8/3, divided by 1 minus 16/9. Okay, so I could multiply everything by 9 to get rid of those denominators like a complex fraction. But in this case, I'm actually just going to rewrite this as a 8/3 all over 9 over 9 minus 16/9. So by rewriting 1 as 9 over 9, I can now combine these. So therefore, that's going to give me a 8/3 all over a -7/9. Now, what's important is I can rewrite that as a 8/3 times a 9 -7. So that divides a 3, and that gives me a -24/7. So yeah, you can just do 8 times 9 and then divide it by -21, or obviously 3 divides a 9 3 times. 3 times 8 is 24, and I just brought the negative out in front. So sometimes it might be a little bit easier to do fraction operations that way, right? Instead of dividing, I multiply by the reciprocal, just kind of going through that steps. But you could also multiply by 9. That's what I did last chapter or last section. All right, the next thing we're going to work on is verifying some identities. So, remember when we're verifying identities, we basically want to make the left side look like the right side. And there are many ways that we can go ahead and do this. Sometimes it's helpful to just, when you see a double angle formula or a half angle or a sum of difference, is just to plug in that formula and then kind of work from there. But in this case, I kind of recognize that you always want to pick the side that's the more complicated. And you want to look for either operations or identities you can immediately obtain. Now, again, these don't divide out, right? So we got to think, all right, what can I do? And I recognize a tangent squared. And typically when you see a trigonometric function squared, you want to think the Pythagorean identities. And I recognize 1 plus tangent squared is secant squared, so I'm just going to roll with that. And let's see what we can do from there. Okay, and it doesn't look like that really helps us much. But the next thing I'm going to think about is say, all right, so I know my double angle formulas for cosine. None of them are fractions. That means if I need this to look like this, I need to get rid of this to be a fraction. So one way is you could divide the secant into both those terms, but I think for this way, it'd just be easier just to multiply the top and the bottom by cosine squared of x. Right? So if I multiply the top and the bottom by cosine of x, that's multiplied by reciprocal, that's going to make that 1. And then, of course, just remember to multiply using distributive property. So therefore, that gives me a cosine squared of x minus a tangent squared of x times cosine squared of x. All right. Now again, we know there's one of them is cosine squared minus sine squared. So does this give us sine squared? Well, let's just use our identities here. And hopefully we're at that point where we could maybe recognize this without writing that out. But for maybe the students that need it, you can see that, hey, they do divide out. So therefore, we're left with a cosine squared of x minus sine squared of x, which is equal to a cosine of 2x. And there you go. We have verified we made the right-hand side look like the left-hand side. On for the next one. That looks really kind of fuzzy. It's kind of weird. It doesn't look fuzzy on my computer before, but I guess when I print it, it is. So in this case, I recognize here the sine, right? So 1 minus cosine squared of x. Again, the right side looks more complicated than the left side. So I'm going to work on this right-hand side. I see a 1 minus cosine squared of x. I recognize that to be the sine squared. And then obviously if I need to get this to be tangent, I need to go ahead and apply that identity. So I'm going to apply the trigonometric or the Pythagorean identity up top. So that's going to be a sine squared of x all over a 2 sine of x cosine of x. Okay, so I have the 2. That's nice, right? I needed a 2 in the denominator, so it's nice that's where that came from. Now, the next thing I need to think about, all right, so the tangent is sine over cosine, right? So I have a cosine in the denominator. I need to somehow get rid of my sine here. Now, you could just like cross things out and call it's good, but let's kind of see where this kind of comes from. So what I'm going to do is I'm going to rewrite sine squared as sine of x times the sine of x all over 2 sine of x cosine of x. Now you can see the sine of x's divide out, right? It's the exact same expression divided by itself. And then you can see my sines of cosines. Oops. My sine of cosine divides to tangent. So that's going to leave me with a 1/2 tangent of x, right? I just wrote that, or sine of x over sine of x, right? Remember, divides to 1. So you can see where that 1 comes from. And then you have the 1 divided by 2 tangent of x. And you can see that's beautiful. You could write it, you could leave the 2 underneath, or you can just write it down in front. Either way, we are verified. All right, so then we just kind of work through a couple more examples with the students in class. So let's just kind of look through these examples here. So the first one is sine squared of x plus cosine squared of x. Now, again, here's a tricky part, like which identity do you use, right? So this one's kind of tough. Like it really comes into a play here. I would recommend, since I'm trying to make this look like the right side, I know that cosine squared minus sine squared, right? That minus sine squared is going to get rid of the sine, right? So because I need to get rid of this sine squared. And you could use your Pythagorean identity to convert that to a cosine, and then you'd use a different, then you could use a different trig identity for this one. But just the way that I initially look at it, and again, you could do all three of them. It doesn't really matter. Just some are going to be maybe a little bit more difficult than the others. But I wouldn't want you to be, just kind of paralyzed by like, I don't know which one to pick. Just pick one and roll with it. But the reason I saw this one as being, and typically I always like to look for cosine squared of x minus sine of x. I always look at that one first to see if that's going to be helpful. And this one actually becomes, pretty easy because those are just going to go ahead and divide out. And you can see that's verified. So it really wasn't that much of work. And again, it might just be maybe an extra step or two if you would have picked the other ones. But I always pick cosine squared of x minus sine of x first. And before I move to the other identities, unless I recognize something that might be helpful for the other ones. The next one is, you can see the left-hand side is multiplication. So it's like, all right, well, let's multiply them, right? I mean, I don't know what else I can do. Make sure you do not distribute. I was actually so happy my students, none of them distributed the square root, right? They actually multiplied these. They did sine of theta minus cosine of theta times sine of theta minus cosine of theta. Yeah, why did I do that? Now, this one is not as fun to distribute, but you can see here we get a sine squared of theta. This becomes a negative sine of theta cosine of theta. This becomes a minus a cosine of theta sine of theta. And this becomes a positive cosine squared of theta. Now, again, we recognize this. That is our Pythagorean identity, so that becomes 1. And then these are the same term. Even though they're not in the same order, they are the same expression. So we can say a minus a 2 sine of theta cosine of theta. And again, it's like the same thing, guys. It's like if I have x minus y minus yx. Well, that's equal to a 2. I'm sorry. That's equal to a negative 2xy, or, which is also equal to a negative 2yx. So the order on multiplication is, right, it's not going to matter, right? It's a commutative property. So we can rearrange these any way we want to. And just remember, if we have a negative when we're subtracting, that's going to be that negative 2. Now what we do is we recognize that this is the double angle formula for sine, which is, again, which we're looking for. So 1 minus sine of 2 theta. And there you go. All right, into the next one. So the next one, I'm going to pick the right-hand side. And again, I'm not really sure which one to do, so I'm just going to start with the way that I told you. Do the cosine squared and sine squared. So I'm going to pick the right-hand side because that's where my double angle is. So I'm going to do cosine squared of x minus sine squared of x all over a cosine squared of x. All right. Now again, I can see here that the here on the left-hand side, I'm trying to get rid of this fraction, right? So you could multiply by secant to get into there. That's fine. But I would just distribute the cosine squared of x into both of those terms. So when I do it this way, I think this one's just a little bit easier to see it. You can see cosine squared of x divided by cosine squared of x is 1. And sine squared of x divided by cosine squared of x is going to be a tangent. And there you go. It's verified. So again, like you could have done it, a couple different ways. And again, guys, like verifying, it doesn't matter. You just got to try something. If it doesn't work out, then try something else. So in the next problem, we can see that we have the double angle for sine as well as the double angle for cosine. Now, obviously, the right-hand side is going to be more difficult than the left-hand side. Now, the trouble here is, again, like which cosine formula are we going to use? And actually, the only one I didn't really work out all the way because it actually seemed to me is the more difficult one would actually be writing this as cosine squared minus sine squared. So I actually thought about this a little bit different way. And the way that I came up with was using, like, if I want the right-hand side to look like the left-hand side, I don't want this plus 1. So I want to use the identity that's going to actually try to eliminate that plus 1 by actually adding a negative 1. So if you look back into the identities, you recognize that the other one that's only in terms of cosines has a negative 1 with it, or you're subtracting a 1. So what that will do is that will add with that 1 to give us a 0. So let's work it out and I'll show you. So again, that's just me thinking ahead. Some of you probably will not be thinking ahead like that. So again, it just comes and try something. Doesn't really seem like it's going to help you out. So then pick another one. But here I kind of looked ahead and I recognize cosine of 2x, I can rewrite that as 2 cosine squared of x minus 1. So now what happens is my 1 and my negative 1 goes to 0. So therefore that's going to leave me with a 2 sine of x cosine of x all over a 2 cosine squared of x. Now you can see my 2's divide out, right, to 1. I have 1 cosine of x up here. I have 2 of them down here, so I'm just going to divide 1 of them down here with the 1 up there, which just leaves me with a sine of x over a cosine of x, which is equal to a tangent of x. All right. All right, so the last one we kind of worked on is the solving using these double angle formulas. And again, this one's a little bit difficult in the case of, again, like which one do you pick? Now, here I do have a little advice for you. Typically, when we want to solve, we want to keep things in terms of the same trigonometric function. So if I already have a cosine, I don't want to introduce sine. So I'm going to, again, use the trigonometric function that is already in terms of cosines. So I'm going to use 2 cosine squared of x minus 1 plus cosine of x equals 0. Now again, this starts to look a little familiar. I'm like, what do I recognize about this equation here? What does this look like? Well, if you just kind of forget that you're dealing with cosines for a second, you can see that this looks like a quadratic trinomial, right? And we can solve these by factoring. So remember, all quadratic trinomials can be factored into a product of 2 binomials, right? And so therefore, all we're looking for is what two numbers multiply to give you the first two terms, 2x and x, and what two numbers multiply to give you -1. Now again, our options, guys, are -1 and +1, or -1 and +1. So we don't have many options. So really, you can just do a guess and check from here. But if we want to kind of think strategically about this, what you want to do is say, all right, here are my inner and my outer products. If my middle term is positive, then the larger of my two products also has to be positive. So again, I'm going to be multiplying a 2x times a 1 and a x times a 1. Well, which one's going to be larger? Of course, 2x times 1, right? So I want that one to be positive, and therefore this one can be negative. And again, let's like multiply it out. That's 2x squared, right? Minus x plus 2x minus 1. So you can see, since the larger of my two products is positive, that's why that produces a positive x, which I am looking for. Now, all we're simply going to do is go ahead and rewrite this, or rewrite the factored form with cosines of x. So we'd have 2 cosine of x minus 1 times a cosine of x plus 1 equals 0. Now we can apply the zero product property, right? Because if we have now a product equal to 0, we can apply the zero product property. So therefore we have 2 cosine of x minus 1 equals 0, and we have a cosine of x plus 1 equals 0. Therefore, cosine of x equals positive 1/2. Cosine of x equals -1. And now just going on the unit circle, we can say that, on the intervals from 0 to 2 pi, we can say that actually, let's write out the unit circle. Okay, looking at the unit circle, cosine's positive, so it's going to be to the right of the y-axis at 1/2. It's going to there and there. So A will be, let's see, that solution is going to be pi over 3 and 5 pi over 3. And then with cosine of x is equal to -1, that's going to be this point over here, right? -1, 0, which is going to be at pi. And then the last thing is, if we want to find all the solutions, and we recognize that these are actually a distance, like, are these equidistant from each other? And yeah, it does kind of look like they are equidistant from each other. Let's kind of use a different color here. Right? So you can see that they kind of look like they're split up into thirds. And again, like, let's see, like, this is pi, which could be written as 3 pi over 3. So if you're at pi thirds, and then the distance from pi thirds to 3 pi thirds is 2/3. And then here we have 3 pi over 3 to 5 pi over 3, which is again 2/3. So yeah, the answer for all our solutions, you could just take each one of these and add 2 pi to them, but that's a lot of writing. So what I told my students to do is just take pi over 3 and add 2 pi over 3n. And there you go. That is all the solutions. Now in the next example, there's really not much we can do. Like, a lot of students sometimes say, oh, well, can we just use the square root of 3 product property? And I say no, because that's not a property. So we have a product equal to a number that you can't use that like we did for the zero product property. We can't factor out something. They don't have anything in common. Remember, the cosines of x's, so you can't factor that out. You can't multiply them. There's really not much we can do. So we go back and look at those formulas and we say, well, it kind of looks similar to the double angle formula for sine, right? But that was 2 sine of x cosine of x. So what else could we do? Well, we could rewrite 4 as 2 times 2. And by doing that, now we can just say, well, you know what? I like u2. I only like this 2, not this one. So we could just kind of exclude the other one. And therefore, now we could take this one and rewrite it as 2 sine of 2x equals the square root of 3. Then we just divide by 2 to isolate our trigonometric function. And now we can just go ahead and use the double angle here. So again, when we're doing the double angle, we want to find all the solutions first. So looking at the unit circle, we can say that sine of 2x is going to equal the square root of 3 over 2. That's going to be at here and here. Okay, now again, these don't have any symmetry with them, so therefore we are going to let's see, we need to add 2 pi n to them. Right here, they had symmetry, or not symmetry, but they're equidistant. So you can add the same distance to each of them. These, they do not have that. So therefore, we have to add 2 pi to each of them. So 2x plus 2x equals 2 pi over 3 plus 2 pi n. All right, now we'll just divide by 2. And therefore, we're left with x equals pi over 3 divided by 2 is pi over 6 plus pi n. And then here we have x equals, again, now 2 pi over 6 can be reduced to pi over 3 plus pi n. And then if we want to find all the solutions between 0 and 2 pi, basically what we're going to do is we're just going to, again, add intervals of our solutions. Intervals of n, right? Because now you can see every solution is going to occur every n. So n or every pi. So we have pi over 6. And if we add pi to it, that'd be 7 pi over 6, which falls between 0 and 2 pi. But if we add pi again, that would be 13 pi over 6, which is too large. So then we move to the next angle, which is pi over 3. That works. And if we add pi to it, that's 4 pi over 3, which that works. But we can't go any farther. So therefore, we'll end it at there. All right. And then we just add a couple more equations to kind of work through. So let's just go and get started there. So in this first case, you can see I can rewrite this as 2 sine of x times the cosine of x minus the sine of x equals 0. And now I can factor out a sine of x. That's going to leave me with a 2 cosine of x minus 1 equals 0. Now I have a product equal to 0, and I can apply the 0 product property. Okay, and then that can go and equal cosine of x minus 1 is equal to 0. And now basically we just want to look at the unit circle. And again, we're going to find the values between 0 and 2 pi. Right, so we have when sine is equal to 0. Well, sine is going to equal 0 at these 2 points. And we have when cosine is equal to 1/2. I don't know why I solved it like that. But we're looking for when cosine of x is equal to 1/2, which is going to be at pi over 3 and 5 pi over 3. Okay, now these do not look like they are going to be equidistant from each other. So therefore, I'm just going to list them out. So we'll have 0, pi over 3, pi, and 5 pi over 3. Let's see here. Now I could add these. That's kind of interesting. I guess what I'll just do, I wonder about that because, yeah, those aren't equal. Those are the same. I wonder what the best way to do that would be. Because I do have pi n. It's really 0 plus pi n you could do. I don't know why I put the 0 there. So you could just do pi n. And then we could do pi over 3 plus 2 pi n, and kind of running out of space here, 2 pi over 3. I'm sorry, not 2 pi over 3. That's 5 pi over 3. Then you can do 5 pi over 3 plus 2 pi n. So kind of ran out of space. Apologize for that, but those two are there. Now this next one, again, kind of comes to that point that we were talking about as far as writing them with the same trigonometric function. Like I don't want to use cosine squared minus sine squared here because I already have a sine squared. So what I'm going to want to do is use the one, and again, I'll just want to make sure I write this as use the trigonometric function where I'm in terms of sines. So that's going to be 1 minus 2 sine squared of x. So I have sine squared of x minus 2 equals 1 minus 2 sine squared of x. And again, let me just go ahead and make sure I had that right because I kind of already forgot. That's going to be 1 minus 2 sine squared of x. Okay, perfect. All right. And now in this case is, let's go ahead and add the 2. Then we'll add a 2 sine squared of x here. Okay, so now we have a 3 sine squared of x equals 3. Well, I'll divide by 3. And I have a sine squared of x equals 0. And obviously when you take the square root of 0, you're just going to be left with a sine of x equals 0. So we already did that over here. So when sine of x equals 0, that's going to be at 0 and pi. So for a, I'm just going to have 0 and pi. And then for all the solutions, it's just going to be 0 plus pi, 2 pi, or 0 plus pi n. Or we could just say pi n. All right, for the next one, in this case, I am going to, now this one's kind of interesting. You could go and convert them to the same, but I know basically I'm solving, I'm trying to isolate either my variable or my trig function, or I want to set it equal to 0. So I'm just going to set this equal to 0, and I just, I kind of recognized here that, I have cosine squared of x minus sine squared of x. I can rewrite that as the cosine of 2x equals 0. Now I can apply that double angle formula. Like now I just got to see when is cosine of x equal to 0. So I'll find all the solutions first. Well, cosine of x equal to 0, that's going to be at 2x is going to equal to pi halves plus pi n. Because again, if you go back to the unit circle here, it's going to be 0 here, pi halves and pi n. That's when cosine is equal to 0. So I'll just divide by 2, and I get x equals pi over 4 plus pi halves n. Now to find all the solutions, all I'm going to do is just add pi over 4 plus multiples of pi halves, which in terms of pi, or in terms of n, or in force, would be 2 pi over 4. So I have pi over 4, and then I could add pi halves again, which would be 2 pi over 4. 2 pi over 4 plus pi over 4 is 3 pi over 4. And you're going to keep on going until you can't go above 2 pi, which would be 8 pi over 4. So I have 5 pi over 4 and 7 pi over 4. Okay, so I kept on adding pi halves to pi over 4 because n represents, your those additions you can make, and you keep on going up to as far as you can go. For the next one is, again, I see this as cosine, but I kind of have an idea here that I'm going to want to divide this cosine squared out of the denominator. So what I'm going to do is I'm actually going to write this as cosine squared of x minus sine squared of x divided by cosine squared of x equals 1. Actually, that doesn't work. That'd be 1 minus tangent squared. I was thinking that'd be 1 minus tangent squared of x. Okay, yeah, that works. What am I thinking? So yeah, this is 1 minus tangent squared of x. You could subtract 1 here. So then I have a negative tangent of x equals 0. So divide by negative 1 here. And now we're just going to have tangent squared of x equals 0, square root. And again, you're going to have tangent of x is equal to 0. Well, tangent, remember, is when the y coordinate's over the x coordinate. So let's do another circle here. This point is 1, 0, and this point is negative 1, 0. So again, you can see that the tangent is going to be 0 at 0 and pi. So again, this is going to be the same solution as we had before here, which would be 0 and pi. And then for all the solutions, it's going to be at pi n. Okay, so that kind of wraps it up with how we use the double angle formula. It's helpful to help us evaluate angles, it's helpful for verifying, and it's helpful for solving. So now we're going to get into the next type of formulas, which look a lot crazier and more difficult, but they're really not as bad once we get into the work, and that is the half angle identities. So I wrote this twice, and it kind of seems to be a confusing part, so I'll try to do my best to explain why we have this plus or minus and when to determine the plus or minus. And it's really actually basic. I mean, when this half angle, whatever you're taking the sine, the cosine, and tangent up, or not tangent, but whatever you're taking the sine over the cosine, whatever that half angle is, like for sine, if it's in the third and the fourth quadrant, then sine is negative. If cosine, if that angle is in the second or the third quadrant, that's like to the left of the y-axis, that means the half angle is going to be negative. So it kind of gets confusing. That's why I always kind of tell students that, hey, I can explain it the best I can, but sometimes it's also just helpful just to do some problems and then explain it again there. So you can see these formulas, though, are very similar to each other. Obviously, the only difference between sine and cosine is a negative, right? Instead of you're doing 1 minus cosine compared to 1 plus cosine. And then for tangent, you have, really, it's just kind of like these reciprocals. Sine of theta over 1 plus cosine of theta is equal to 1 minus cosine theta over sine of theta. And this is something that we've actually already proved. If you remember, this is something that we did before. So we've actually proved this as an identity. And again, that comes from that half angle formula. The other thing I'd like to point out is typically when I'm applying the tangent, the half angle of tangent, I like to use this one because I prefer to have just sine in the denominator rather than a binomial 1 plus cosine of theta. So either way, now let's go, that's the formulas, and now basically we're going to apply them to evaluate. So again, kind of like what I did before, I'm going to give you one of these, and then we're going to work to apply one of these. Now this one, we're going to evaluate if possible. Now you could obviously evaluate all of these as they are in their equation. But the point that I want to try to make to the students is to understand what actually is, if we can write this as a single trigonometric function, right? So it says simplify the following trigonometric functions by really writing this as a single trig function and then evaluate if it's possible. So usually these expressions look kind of crazy. All right, so the best thing to do is just understand, all right, here's my angle, right? So we could say theta is equal to pi halves. Now, if I'm going to write this as a single trig function, we know that this is going to be a half angle, right? So it's going to be sine of, theta divided by 2 or cosine of theta divided by 2. So I recognize that this looks like the 1 minus cosine, so that would be the sine formula. So this is the sine half angle formula divided by 2, right? That's the formula of sine. Now all we got to do is plug in the half angle. So really we can say the sine of pi halves divided by 2. Well, again, divided by 2 is the same thing as multiplying by 1/2. So that's equal to the sine of pi over 4, which is equal to square root of 2 over 2. So the important thing, which is what this is bringing up here, is that, if you remember from the double angle formula, when we were given our theta, we just multiplied by 2. Whereas now, when we're given our angle theta, we're dividing it by 2, right? Because it's the half angle formula. So hopefully you recognize on this one is the cosine formula. And so therefore, to write this again, you can recognize this as the half angle formula. And when you divide this by 2, it's going to be 150 degrees. Now, here's one explanation you can see why this is negative, right? Because when I take the cosine of 150 degrees, or if I was to take the cosine of 150 degrees, I know the answer is going to be negative. So that's why we make sure that radical is going to be negative. Now we can just evaluate for 150 degrees, which again has to have as a reference angle of 30 degrees, which is going to be the same as 5 pi over 6. So therefore, you could say that's going to be a square root of 3 over 2, but since it's in the second quadrant, it's a negative square root of 3 over 2. Okay? And now for the last one, you can obviously see this is going to be tangent, right? And you just divide that by 2, but we kind of have a little issue here. Tangent of 75 degrees. I can't evaluate the tangent of 75 degrees. So I'm kind of stuck, right? So what I'm going to do is I'm just going to go back to, well, why don't I try to simplify this, right? If I want to evaluate, I want to find the value. So I can't evaluate the half angle because I don't know the 75 degrees. So unless I did like the sum and difference, right, formula. So what I'm going to do is I'm just going to evaluate this. So we know the cosine of 150 degrees. I just did that right there, right? So that's going to be a negative square root of 3 over 2 divided by the sine, which is 1/2. Now, again, if I needed to evaluate this, I could just multiply by 2 on the top and the bottom. And therefore, that would leave me with 2 plus the square root of 3. And there you go. That's how you can evaluate. And that's exactly what we're going to be doing for the next set of problems. So typically, that's when you're going to have an angle. Now, the next one we're going to look at is dealing with or using the half angles to evaluate with some other angles in radian form. All right. So on this first example, basically, we just need to understand, really, I think the most difficult portion to understand here is what our angle is. So remember, we're going to evaluate using the half angle identities. So therefore, we can say u over 2 is equal to pi over 8. Now remember the formula here for sine is going to be plus or minus the square root of 1 minus the cosine of u divided by 2. That's it, right? So if we're going to say this is u over 2, then we just need to figure out u then is going to be pi over 4. Well, let's just break it down. We'll do this first one. So that's going to be 2 pi over 4, right? Because you're just going to multiply by a 2 on both sides. So therefore, u is equal to pi halves. All right? I'm sorry, pi over, I was thinking two other things. So we have 2 pi over 8, which gives us a pi over 4. Now, the next thing is, once we've identified u, our angle, or theta, then we just need to determine, is it plus or minus? Well, again, for sine and cosine, you have to determine where the quadrant of that angle is. Pi over 8, right, is in the first quadrant. Again, 8 pi over 8 would be pi. 4 pi over 8 would be pi halves. So again, for sine to be negative, it would have to be larger than pi, right? So it'd have to be in the third and the fourth quadrant, which this is not. So now all we're going to do is just simplify here. So that's the positive version of 1 minus the cosine of pi over 4 divided by 2. All right, well, the cosine of pi over 4 is going to be square root of 2 over 2 divided by 2. Now, typically, that is evaluated. We can just typically simplify this a little bit more. We could multiply by 2 over 2. And I'll just do a little work here because I'll skip some steps later. Make sure you put parentheses here because you're going to distribute. So that's going to be 2 minus the square root of 2 over 4. Remember the rules of radicals, which is 2 minus the square root of 2 over the square root of 4. The square root of 4 is 2. So then typically we would see this answer written like this. Okay, so therefore you can see one example in that case. Let's go and do it again. Now we have an example of cosine. So again, just going to do the same thing here. We notice that pi, so therefore u over 2 is equal to pi over 12. So therefore u is going to equal pi over 6, right? When you multiply by 2 on both sides, you have 2 pi over 12, which is pi over 6. I don't know why I'm writing over 12 or over 2. In the next one here, we recognize that pi over 12 is in the first quadrant. So therefore my angle here is going to be 1 plus the cosine of pi over 6 divided by 2. Okay, so again, we're just going to do the same thing. Now you can say that, all right, that's going to equal 1 plus pi over 6 is going to be the square root of 3 over 2 divided by 2, multiplied by 2 over 2. Again, make sure you put those parentheses. So it's 2 plus the square root of 3 over 2. And then hopefully you recognize, over 4. And then again, we can do the same thing. Square root of 4 is going to be 2. You can bring that out in front. And then in this case, we have 2 plus the square root of 3. So really the only thing that kind of changes here is obviously what is our angle that we're plugging in. And obviously it's plus or minus as well. But then also dealing with, what is going to be that quadrant. But in this case, we're just dealing with the positive angles. And we'll get into another negative one for cosine later. And then let's just go ahead and do the one for tangent. And again, the formula that I like to use for the half angle here of u divided by 2 here is going to be 1 minus cosine of u over sine of u. Okay, so if we recognize here this in case, so if u over 2 is 22.5 degrees, that means you're just going to multiply by 2 is 45 degrees. So now we're just going to plug this into the calculator, 1 minus the cosine of 45 degrees all over the sine of 45 degrees. So we have here is 1 minus the square root of 2 over 2 divided by the square root of 2 over 2. In this case, you could, a couple different ways. First, we could multiply everything by 2 over 2. So again, make sure you put parentheses here. So it'd be 2 minus square root of 2 over the square root of 2. And then we could just rationalize the denominator. And again, you could multiply by 2 square root of 2 if you wanted to, not do it, one by one, but just for kind of educational purposes, I'm just going to show you multiplying it this way. And then now you can see these square root of 2 times square root of 2 is 2, right? Square root of 2 times negative square root of 2 is a negative 2. And now you can see you divide the 2 into both of these terms. So you're left with a square root of 2 minus 1. Okay, so you can kind of see how everything can be simplified out. And obviously you could break some of these up together if you needed to, if you wanted to. Last example here, u divided by 2 is 15 degrees. So therefore u is going to equal 30 degrees. So again, let's just plug it in here. So I have 1 minus the cosine of 30 degrees all over the sine of 30 degrees. So cosine of 30 degrees is going to be square root of 3 over 2 divided by 1/2. And then we can just multiply the top and the bottom by 2. Again, just make sure you're applying distributive property. So that's become 2 minus the square root of 3. So basically, when you're evaluating given an angle, I think it's most important to identify u over 2 so you can identify the u. And then if you're dealing with the sine or the cosine, just make sure you understand the angle on that. Now, for those two examples, we both did the first quadrant. So I think it's time for us to do one more triangle or one more value where it's not in the first quadrant. So the next one is now we're going to have a triangle, which we've done for a double angle as well as for sum and difference. So again, we don't have our angles, right? We have an equation. Secant of beta is equal to 3. Now again, remember all trigonometric functions can be rewritten as a comparison, right? It's hypotenuse over adjacent. So I'm going to draw a triangle on a coordinate grid, x and y. I see here that sine of theta is negative. That means my triangle has to be in the third or in this fourth quadrant, okay? Now, my big thing is I need to determine is which quadrant is it? Well, since secant is positive, it has to be to the right, right? Secant, remember, is a hypotenuse over adjacent. So therefore, the adjacent side is positive, so it has to be to the right. So here's a 3, 1. We'll call this beta. And then now we need to figure out what exactly is our opposite side here. So doing a little Pythagorean theorem, 3 squared equals 1 squared plus, I don't know, let's call this b squared. and therefore you get 9 equals 1 plus b squared, and hopefully you get b equals the square root of 8. So, or we could also write that as 2 radical 2, right? So I'm kind of skipping ahead a couple points for you just to, let's just do it anyways. So you can subtract 1, so b squared is equal to 8, and b equals the square root of 8, which is equal to 2 radical 2. But again, it's plus or minus, right? And since it's in the fourth quadrant, we know it's going to be a negative 2 square root of 2. And that's why that plus or minus is so important there. So let's actually maybe fix that a little bit. Okay, so now we have our triangle. We have all 3 sides. Now we can just go ahead and apply the formulas. So now again, it's actually really important for us to understand this actually isn't our angle beta. That's actually the reference angle beta. And so up to this point, we basically just used the reference angle because it was a lot easier, but really understand this is the angle beta that we are referring to. This is the angle. Just the reference angle is what we've used inside of the triangle. The reason why this is important is because when you look at that angle, like that's our angle beta. If we want to see beta divided by 2, so if we're going to take this angle and divide it by 2, it has to be between the y-axis and the x-axis. It has to be in this quadrant. Because again, like what's the smallest this angle could be? Like 271, right? So if you take 271 divided by 2, it's going to be larger than 90. Or if you took the angle, like let's say 359 degrees, divide that by 2, it's going to be smaller than 180. So it's going to be somewhere in between here. Now again, sine is still going to be positive, but the cosine for this half angle, obviously in the second quadrant, cosine is going to be negative. So when we do the cosine problem, we're going to want to make sure we have it and we make a negative radical. All right, so now all we're going to do is just go ahead and take the formula. So we're going to use the positive version for sine. So 1 minus the cosine of beta. Now again, what's the cosine of beta here? Cosine of beta is 1 over 3. All over 2. Again, all we want to do is really simplify this so we can multiply by 3 over 3. And we get 3 minus 1 all over 6. And again, that's all under radical, right? Which can simplify to 2 over 6. So we can break that down into a square root of 1 over the square root of 3. And square root of 1 is obviously 1, but you could rationalize the denominator here and get a square root of 3 over 3. Now let's go and take a look at the cosine of beta. Remember, this is going to be the negative, right? And it's going to be 1 plus the cosine, again, which is 1/3. So 1 over 3 divided by 2. Now again, obviously we recognize this is really going to provide us with the same type of answers here. So it's going to be negative. We can multiply by 3 over 3. So now it's going to be 3 plus 1 over 6, which is going to give us a 4, which is going to give us a negative 4 over 6, which is equal to a negative 2/3. So therefore, this will give us a negative square root of 2 over a square root of 3. And if we rationalize the denominator here, now we would have a negative square root of 6 over 3. So you can see very similar operations, very similar process. And I apologize for doing the left and then doing the down. It's just kind of how I ran out of space there. But you can see kind of how that process works. All right, last but not least is the tangent. Again, I'm going to use the 1 minus cosine of theta over sine. So cosine is 1 over 3. So I'll do 1 minus my cosine over my sine, which is just going to be negative 2 square root of 2 over 3. Now again, in this case, I don't want to multiply by the reciprocal. I'm just going to do this one at a time. I'm going to multiply by 3 over 3. By doing that, I have a 3 minus a 1 all over a negative 2 square root of 2. Okay, so at least I got rid of the fractions here, and that becomes a 2, obviously. So you can say 2 over negative 2 square root of 2. Those can simplify to a negative 1 over square root of 2. And now I can rationalize the denominator to give me a negative square root of 2, over 2. So there you go, ladies and gentlemen. You can see that as we've kind of done so many examples, really, once you kind of get used to it, the difficulty is not so much in the formulas, but it's into the algebra and the arithmetic of simplifying these. So that is the end of the lesson. Feel free to let me know what you understood, what you kind of still a little tricky from. And it really is just one of those guys that it takes some practice, you know, working with them from angles, working on them from triangles, and looking into how to apply them for verifying as well as solving equations. But I hope you enjoyed, and I look forward to hearing from you and seeing you on the next video. Cheers.